so physicists, what questions do you have over the homework? Things that you would like to go over from the homework? So it was 162, 2 and 5, 164, number 4. Questions on that? Did you have a question, Madeline, you wanted to ask about?
164, number 4.
164, number 4. I didn't hear what you said. Say that again.
I didn't get very far in it.
Okay, let's take a look. So, so 164, number 4. So everybody's looking at it. So you've done it, you know the right answer, or you didn't do it and you're learning it now. Either way, let's talk. We've got the 75 kilogram bobsled being pushed along a horizontal surface by 2 athletes. After the bobsled is pushed a distance of 5 meters starting from rest, its speed is 6 meters per second. Find the force of the net force on the bobsled. So, you started with some givens. So what givens did you have written down?
The mass is 75 kilograms. The distance is 4.5 meters. The speed or velocity is 6 meters per second, and then you have to find the estimate. But then they said it was the magnitude of it, and then I was confused.
Gotcha. Okay, so magnitude just means size. So that means we don't care about a positive or negative.
Okay,
So that's
like
all
the
that.
absolute value.
Yes, exactly. Yep. So is that okay then? Okay, so that velocity. Yeah, okay, so let me back up. If there's a net force on there, is there an acceleration? There's a net force, there's got to be an acceleration. So this velocity isn't a constant velocity. Is that an initial or a final velocity? That's a final velocity? Okay. And what's the initial velocity? Okay. So that's good to know. All right. And then they say go, right? And you're like, okay, go. What ideas? Where are we going to start? I'm going to look at the title of the section, because if I don't know what to do, one of the things to do is look at the title of the section. And so the title of the section says, right at the top, right above where it says practice, blah, blah, blah. It says work kinetic energy theorem. Now, we've not talked about it as the work kinetic energy theorem. We've talked about it as the work energy theorem before. What is the work energy theorem? Do you remember? Look in your notes if you don't remember. Find it, somebody. What is the work energy theorem? We wrote about it a couple of days ago, I think. Yeah. Work is equal to the change in energy. In this case, the kind of energy we're talking about happens to be energy of motion, right? The energy of motion is kinetic energy. So we're doing work on this bobsled to get it to change its kinetic energy. Is that okay? Doing work to get it to change its kinetic energy. So I'm going to say, I'm just going to rewrite this again. I'm just going to write it with a K in it though. So work is equal to the change in kinetic energy, which really means the kinetic energy at the end minus the kinetic energy at the beginning. Okay? All I'm doing is trying to process what's going on. I also know another definition for work. What else is work equal to? Force times. And I wanted that in there because the question was about the force. So you need a force in there somewhere. So this is what I want to know. Do I know how far that bobsled goes? Yeah, we wrote that down. 4.5 meters. Do I know, like, do I have listed the kinetic energy, the final kinetic energy of the object? I don't have it listed, but can I find it? Yeah, because I know that kinetic energy, I'm just going to write myself a little note here. Kinetic energy is what, 1/2 mv squared? And I know the mass and I know the velocity, so I can find the kinetic energy. Can I find the kinetic energy initial? The kinetic energy initial is going to be 0, right? That makes life easy, so I'm just going to get rid of that right now. So goodbye. See you later. And now I'm getting to something that's going to get me where I need to go, I think. So now I've got force times distance is equal to 1/2 mv final squared. And now I think that everything in my expression here, I have in my givens list. Do you see that? So we got d, m, v. We're going for our driver's licenses. I'm looking for force. Okay. Can we keep going, or does that kind of get you where you need to go?
I can go a little bit further.
Absolutely, I can. Yeah. So in order to get force all by itself, right now I'm multiplying force by d. How do I undo multiplying by d? Just divide it up. Yep. So the force is going to be 1/2 mv final squared divided by d. And you can just write it like that. So 1/2 75 kilograms times 6 meters per second. That whole thing is squared. So that 6 is squared. Not the rest of it, just the 6. And then we'll divide that by 4.5. How are we doing? Is that okay? That should give us an answer. This is what number? This is question number 4. I think the answer is 300 newtons is what they have in the book, but that's probably with, like 2 sig figs. So there, you may have gotten something a little bit different, like 2 something. I don't know. What was it?
300.
It was 300. Perfect. There you go. Yay! That was a fun question. What else you got for me? Anything else? Other homework questions that you have before we get started on a few more? From me? Okie dokie. All right. Just a friendly little reminder, you know this. This is what we talked about yesterday. So we've got gravitational potential energy is mgh. We've got kinetic energy is 1/2 mv squared. We're going to focus on this one for a couple of minutes here. It's really easy to multiply, but there are a couple of subtleties in there that I want to make sure that you understand. So I'm going to give you a couple of questions here. I'm going to give you just 2 of these to start. So I've got a frog. You met him before. I would like to know if I hold the frog 0.65 meters above this table. So 0.65 meters, so that's 65 centimeters above the table. I would like for you to calculate for me how much gravitational potential energy does he have. Can you do that? Absolutely. If you do not have a calculator out, I would like for you to get one out. We're going to do lots of calculations today, just real quick calculation stuff. So I want to make sure that you have a calculator so that you can do the calculations. 0.6 kilogram frog, 65 centimeters above the table. How much gravitational potential energy does he have just based on where he's sitting? Again, I would like everybody to do this question. I know that sometimes you're like, oh, but my neighbor's doing it. They're doing a great job. But friends, your neighbor's not going to take your quiz for you, your test for you, right? Hope not. Check with your table mates once you've got an answer to make sure that you didn't make any silly mistakes. Okay? To make sure this makes sense to you. How much gravitational potential energy does that frog have when he's 65 centimeters above the table? It's a very exciting and deep question, isn't it? Thomas is like, so exciting. Did you get an answer, Thomas?
3.8.
3.8? Do you guys agree with him? Yeah? 3.8 what? Joules? He's like, yeah, of course it is. Yeah. Because we did this yesterday. And you're like, right, sure, yeah. 3.8 joules. Energy is measured in joules, just like work is measured in joules, because it's all the same stuff, really. Okay, that was fun. Now, this is going to blow your mind. Are you ready? So now I'm going to take the frog, and I'm going to put him at 85 centimeters above the table. Can you figure out how much gravitational potential energy he has now? Lily's laughing at me. This is not a trick question, you guys. This will be super fast, super easy. You don't have to write it all out. Just figure out how much gravitational potential energy he has when he's at 0.85 meters above the table. Check with your table mates. Make sure you don't make any silly mistakes. Lily's going to let me know when she got an answer. No? You got this. I believe in you. Did we get an answer? So it's 0.6 kilograms times 9.8 meters per second squared times now 0.85 meters. Did you get an answer, Lily? She got 5. Do you guys agree with her? 5.0 joules? 4.99999?
4.998.
Okay, well, we'll call that to 2 sig figs. We'll call that 5. All right. I think they're just looking for a fight. All right, now here's my question. Why did we do this? Right? No, I know that because there's one more question in here. The question I really care about is how much work was done in lifting the frog from that 6.5 or that 0.65 to that 0.85. So here he is at 0.65, and I'm going to lift him. Do you guys agree that I'm going to do work? Right? Apply a force over a distance? For sure. I did some work. I want to know how much work did I do. Can you figure that out? Huh? I believe in you. You got this. Talk to your table. Figure it out. This is why I care. Good. You know, there are things and there are times in life you have to let stuff go. I've let a lot of stuff go. All right. Jacob, how you doing back there?
Good.
Did you get an answer? Why not? So you did get an answer.
I'm still Alex.
So you're saying that Alex's answer is wrong.
No, I got it wrong. I'm still Alex.
Okay, let me know when you're done. Shaw, did you get an answer? You got what? You got 1.9. 1.9 what? Joules? How did you get that answer? Where did that come from?
So I subtracted 0.8 and 0.6 and multiplied it by 9.8.
Wait, say that again.
I subtracted 0.8 and 0.6 and then
0.8.
0.85, 0.65
Okay.
and then multiplied it by 9.8.
So you found a change in height. Is that what you're saying?
Yeah.
0.85. And you subtracted 0.65? Okay. And so then you got 0.2. Okay. And then what did you do with that?
9 times 9.8.
And then you multiplied that height times the gravitational acceleration?
Yeah.
Okay. And is that what got you 1.9? Okay. I want to know how much, so where did that work come from then? And I'm not saying you're right or wrong. I'm trying to understand where your answer is coming from. Does So I think you're almost there. I think you're close, but not quite. Ethan, do you want to? Oh, you just have a question. Go ahead. Well, what was the distance that I traveled? 0.2 meters? Uh-huh. What do you, tell me more words.
If you're trying to find work, you need to, it's work is equal to distance.
Hold on just a second. Instead of having one conversation with one student and then having to do this a bunch of times, I would like to have one conversation with all of you together, okay? So Ethan's gonna talk, he's gonna give us some thoughts, and then we can react to it. Does that sound good? I see some other hands up and some other ideas, and I want it all, but let's do one at a time. So go ahead. What were you saying?
I think what should happen is right.
Uh-huh.
So the height, the change in height will just be the distance.
Okay.
Moved from 0.65.
So what are you advocating for then? You're saying that the work is equal to, how do you find work, I guess is my question. The force times the distance? And so what force are we applying? Mm-hmm. So the force of gravity, does that make sense? So the force of gravity, right? The applied force is going to be equal to the force of gravity. How do I calculate that or find that?
Mass times
Yeah. So I think this is going to be the mass times the acceleration due to gravity to give me that force, right? And then multiply that times the height. So I think you want to do that 1.9 times 6 or 0.6. Is that okay? So go ahead and do that. And what do you get when you do that? Just 1 second. Yeah. 1.14.
Yeah.
Is that okay? Yeah? Okay. But Grace is unhappy, and then Matt, I'm going to come to you because she had her hand up a while ago and she was getting cranky, and I don't want to be.
That's not what we got.
Okay.
We got 1.176.
1.176. When did you do this?
Yeah.
So everybody get a calculator real quick. Just let's plug it in because I don't know. So 0.6, right? Times 9.8 times 0.2. Am I doing those numbers right? Is that correct? So 0.6. Let's just double check here. Yep. Because we're all working together, right? We're not fighting about it. We're just trying to help each other out. So did I write this down the way that you wanted it to be? And Grace, that's how you wanted it to be also, right? And so when you plug that in, what do you get?
Yeah, I got it now. 1.176.
1.176. Okay. It's all right. Third time's a charm, right? Okay. Yes.
Okay. Why can't you just do 5 minus 3.8 joules? Because then wouldn't you get a difference in between the two?
Okay, hold on. Back up for a second. Back that truck up. What were you doing?
Well, I don't think it's right. But
No. Keep talking.
if you take the second distance, which is the 0.85 meters, and we solve that problem to figure out how much potential energy there was.
We did that here, right?
And that was 5 joules. And then the one above it, 0.65 meters,
Mhm.
we found how much was there, and that was 3.8.
Mm-hmm.
So can you just take the 5 minus the 3.8, and then you find the potential energy in between, and that would probably be equal to the work. Not really close.
Is this what you're saying, just in words instead of?
Yeah. Yeah, like that.
It says to find the work, right? And this is a definition of work. Work is change in energy.
Yeah, it just seems like
And then, so the final was 5, is that right? And the initial was 3.8.
so I got 1.2, which is really close to 1.176.
Yeah, if you use the exact decimals, you get the.
You get 1.176.
Yeah.
So instead of rounding the 5.0 and the, yeah, okay. Okay. So I like this problem for a couple of reasons. You get the same answer, right? Which one's right? Both. You're doing exactly the same thing. Okay? There are two ways to solve the problem. Both of them are correct. Both of them are legitimate. Both of them are good physics. The reason I wanted to show this to you is because sometimes there's more than one right way to do something. And it's really important to know that, like in life, but also in physics. But I also want to just kind of point out to you, so the potential energy when you calculated it earlier, literally what you did earlier was that you said MGH final, right? This is MGH initial. This right here is exactly the same as this. Do you see that? So it's not even that you're doing different, it's just a different like spin on the same story. You're just taking a difference here as opposed to finding the difference there. Both of them are fine. Sometimes it's easier. That's what you're arguing. It's easier to do one over the other. That's totally cool. Yeah, it just depends. Depends on where you're at and how you're looking at something. And it's okay to look at it two different ways. Okay, I've got another like follow-up to this. So actually, I'm going to go back up here so we've got our numbers that we had here. Okay, so here is my frog. 65 centimeters above the table. I asked you a minute ago when you calculated it, am I doing work when I lift it from 0.65 to 0.85? Sure, I am doing work. And as I do work, I'm changing the energy, right? Everybody's happy with that? Okay, now I have a question. We talked about this last week, I guess. If I walk with the frog like this, am I doing work on the frog? Which way is my force going right now? Up. And which way is the displacement happening? This way. And so if I've got force in one direction and displacement in a different direction, they're perpendicular, then no work is done. Right? Okay, so now here's my question. So I've got my frog, and he's sitting here at 0.65 meters above the table. Okay? Everybody's happy with that? And how much potential energy does he have right now? 3.8 joules, right? How much potential energy does he have now?
Wait, are we going from it like based off the floor up there, or?
I'm just looking at him here. He had 3.8 joules of energy, right? And so I want to know how much energy does he have here? What?
I said more than 3.8 joules.
More than 3.8 joules? But if he has more than 3.8 joules, that means that I had to do work on him. Because in order for the energy to change, then work has to be done. But you just told me that no work was done.
So would it be the same potential, like energy, since it's the same distance from the surface of the Earth? It's just that there's something in between.
Right. That's the trick. And somebody just said that too. It's weird because you want there to be more than 3.8 joules there, right? Grace, why do you want it to be more than 3.8 joules? Yeah, it's more than a meter now, right? It's like a meter and some. That's a lot of distance. So this looks like it should be way more than 3.8 joules. But I didn't do any work. So that's weird. And it has to do with where you're calling your zero. You with me there? Okay. So here's the funny situation. So if we draw, I'm going to draw this picture and you can go ahead and draw it too. Here's my floor. And here's my table. And here's my frog. And he's some distance, 0.65 meters above the table. And in doing that, we're really saying that the surface of the table is where h equals 0. But then when I walk him over, doop, 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 so now he's sitting over here, it looks like he's a lot higher, but no work has been done. But my h equals 0 is still here. Does that make sense? My h equals 0 is still here. So that means that if he lands down here, if I let him go and he falls down here, what does that mean about his potential energy now? Gravitational potential energy here. Any idea? It's what'd you say?
Negative.
It's negative. It means that underneath my H equals 0 is going to have a negative potential energy. That's weird. That's weird. We don't usually think about them as being negative, but absolutely, you can have a negative potential energy if your object is below wherever you set your H equals 0. Here's the fun story. You can set H equals 0 wherever you want it to be. You have that power. Lily's like, sweet! Like I can do whatever I want, right? And the reason for that is because it doesn't matter. But you have to talk about it relative to a spot. Okay? We're going to look at another problem that's kind of like this. Thinking towards summer, or at least riding a roller coaster somewhere that's warmish. So here's the situation. Just to make our life really easy, for this problem, to make our life really easy, so we don't have to do a lot of like hard thinking, I'm going to set the acceleration due to gravity at 10 meters per second squared. Is that okay? Because then there are no like 9.8s to deal with. So the situation says we've got a 1,000-kilogram roller coaster car. It's going to move from point A up to point B. And as it does that, it's going to gain potential energy, right? Work has to be done. If you've ever ridden a roller coaster, you know that chain is doing work on the car to get it up here, okay? And then it's going to down here. It's going to have some potential gravitational potential energy here as well. And the question asks you to calculate those. In part A, it says, take your H equals 0 to be right there. Would you go ahead and do that, please? So your H equals 0 is at that yellow line. Could you please find the gravitational potential energy at B and the gravitational potential energy at C? Again, make your life easy, easy, easy. Use G equals 10. MGH. Write it down. Probably don't need a calculator because it's just a bunch of zeros. Okay? I think you can do it. Talk to your table mates. Talk to your physics friends. You got this. You guys are so quiet today. Why are you getting your calculators out? Multiplying by 10 a bunch of times. I mean, I'm not like mocking you, but I'm just saying. What's the gravitational potential energy at B, friends? Can we multiply by tens a bunch?
Is it 100,000 joules?
100,000 joules. There are going to be 1, 2, 3, 4, 5 zeros. 1, 2, 3, or there's 3, 4, 5. 100,000 joules. Yeah, look at that. 100,000 joules of potential energy. Boom. How about at C? Again, you've got your 1,000 kilograms. 10 meters per second. Make your life easy. Meters per second squared, excuse me. Now, what's the height at C? What is it? Negative 15 meters. Talk to your table mates. Figure it out. Write it down. Make some noise. Clay, how many joules do you have?
Negative 150,000 joules.
Life is good? Issues, questions, concerns? Okay. Part B says, what is the change in potential energy? We're literally just going to calculate the change in potential energy. Change in potential energy means final minus initial. So that literally just means negative 150,000 minus 100,000. What is the change in potential energy? You don't need a calculator for that, do you? What do you get, Madeline?
Negative 250.
You got some zeros though, right?
Yeah, 1,000 joules.
Yeah. 250 kilojoules. Yeah, you could be fancy, right? Yeah. All right. Question C says to repeat parts A and B, but take the reference point to be at the bottom. So this is what the problem said to do. This is what Lily wants to do. Because she's ornery sometimes, right? Maybe just now and then. She says, Miss Carling says I can say my H equals 0 wherever I want. Maybe it wasn't in that high a voice, but you get the idea, right? So she's going to put it down here. Now, I don't want to go through all the process. I don't want to figure out all of the pieces. I want to know what is the change in potential energy if I call my H equals 0 here. What is the change in potential energy going to look like? Do we need to figure it out?
Yeah.
Do it. Go, go, go. Do the problem. So if you're sitting next to somebody, you could do one and they could do the other one. Take C if you get a choice. Take C, right? H equals 0. Boom, done. Potential energy at B is M times G times what's the height on B then? 25? Yep. What's the potential energy at C? 0. And what's the change in gravitational potential energy? I heard.
50,000.
There you go. So this is the nice piece of the story, okay? The nice piece of the story is, regardless of whether you're going to follow the instructions and take H equals 0 here, or you're going to be silly and put H equals 0 here, or you can put H equals 0 wherever you want. You can put it up at the clouds. It does not matter. Your change in potential energy every single time will be the same. Okay? It will be the same. That's the nice piece. Is that okay?
But does it matter if it's negative or positive?
This one is actually negative too. I just didn't write the negative sign. Because the final is 0. So 0 minus negative 250,000. Yeah. We okay? All right. We have not a lot of time. I don't remember yesterday. You guys worked on one of these, I think. Did you work on this frog one? The kinetic energy frog one? Did we get to do the one with the car or no?
No.
Okay. I would like to do this with you really quickly. Then that will be perfect. That will be perfect. The question says, what is the velocity of a car with a mass of 670 kilograms whose kinetic energy is 4 times 10 to the 4th joules? So this is taking the kinetic energy equation, solving for V, which is the hardest thing to solve for. But I believe in you guys. You got this. Talk to your table mates because they're so quiet today. Holy cow. an answer, check with your table, see if they agree. Check with your partner. Lily, did you get an answer? What'd you get? 10.92? We need to work on your confidence in yourself, my dear. Cool. All right, friends, you have got some homework for tomorrow. We'll work on some new stuff tomorrow. Have a fantastic day, you guys.